And this is what we see when we start exposing those plates to freezing precipitation. This is what the test apparatus looks like. Here you see plates of our aluminum-coated, asphalt-coated plates on the test apparatus that holds those plates at a constant temperature. There's another photograph of that. Now, if the plates do not have any de-icer on them, what we see is that there is a very rapid accumulation of this white snow-like rime ice. Now compare that to what you see if there is a de-icer liquid on the plate. These plates were treated with plain salt brine. Notice that after 20 minutes of freezing precipitation, there's none of that white rime ice. There's just a layer of brine on the plate. That shouldn't surprise us. That's just what we would expect. The de-icer is melting the incoming freezing precipitation. As the precipitation continues, more and more freezing rain comes down, and it steadily dilutes my de-icer until at some point it's diluted so much that it can't prevent freezing anymore, and it freezes, and I get a layer of transparent glaze ice. Now, we know transparent glaze ice is a bad thing, but here's the interesting thing to note. Under these conditions, as this ice is forming, when it initially forms, how hard do you think it's bonded to the pavement? It's actually completely unbonded at this point. You can take your finger, you can just push it off. So a really interesting thing this points out, and this speaks to the importance of anti-icing, is it takes much less chemical to prevent bonding than it does to either melt ice or prevent water from freezing. So at first you form this transparent glaze ice that's non-adherent, then we continue to expose it to more freezing precipitation. That transparent glaze ice layer grows until at some point now there's a transition. And note now we start seeing the beginnings of this same white rime ice that we saw when there was no de-icer present. So that raises an interesting question. What's the difference between rime ice and glaze ice? Rime ice is dry, fast ice. You get rime ice when precipitation freezes essentially instantaneously when it hits a cold surface. Glaze ice is what occurs if the precipitation freezes relatively slowly, like if it hits a surface that's got a de-icer on it. So in our test, we're seeing a distinct transition from the type of ice formation that we see when there's de-icer present to at some point that surface acting like there's no de-icer present. So does that mean that this transition to the white rime ice would that be a useful test indicator to measure the relative length of time different chemicals can resist being diluted from their effectiveness as anti-icers? Well, further work is needed to answer that question. We need to better understand the relationship between the test results we're seeing here and what happens in the field. But it's an interesting observation. And we also saw that there are certain additives you can put into brines that seem to greatly extend the length of time until that transition to the rime ice occurs. So this shows you an illustration of that. These are plates all treated with salt brine, exposed to 2 hours of freezing precipitation in the test. Plain brine, you see, with no additive, we had a significant accumulation of white rime ice after 2 hours. These other brines had various high molecular weight organic polymers. This would be like xanthan gum as an example. And these typically cause thickening of the brines. And what we found is that some of these dramatically increase the amount of time until the rime ice occurs. So you can see I've got a lot of rime ice on my control plate, but some of these have almost none. So some interesting things there that we are going to continue to explore more fully. And I believe my time is done, I think. We go till 10:20? I'm sorry, 10:20, is that when I'm done? Or do I have 5 more minutes? I got 5 more minutes? Okay, in that case, since I've got 5 more minutes, I'm going to just briefly touch on corrosion inhibitors.